Okie dokie. So let's go ahead and move on to exponential function graphs. In this section, we are going to be looking at graphing exponential functions and then doing transformations on those graphs. Okay, so there's two types of exponential functions we can have. We can have an exponential growth or an exponential decay, and that is just dependent on what base we have. So notice here we are using an example of 2 to the x. Here we're using an example of 1/2 to the x. So we have exponential growth if our base is greater than 1. Okay, so we have something like 2, 3, 9, e, pi, right? Any number that has a value greater than 1 falls into this exponential growth. And then we get an exponential decay if our base is between 0 and 1. Okay, so I'm going to just show you these two examples. One, so that you see how to make an XY table for any exponential graph, and then also so that you can see what the general shape looks like for whenever you start doing these on your own. Okay, all right, so let's look at 2 to the x. And I'm just going to plug in these x values. Most of the time when we graph these, we want to have 5 values just because it makes our sketch a little bit prettier and it makes it easier to analyze our graph once we have it plotted. Okay, so if we plug in a -3, 2 to the -3 power, that negative exponent, remember, flips it or moves the base across the fraction line. So what this looks like now is 1/2 cubed. Right? 1/2 cubed just becomes 1/8. Then I want to do the same thing with -2. If I raise 2 to the -2 power, again, that negative is going to flip it, and then I'm going to square the 2. So 1/2 squared is going to give me 1/4. Okay, so notice it's almost like I'm just taking this 2 and raising it to these powers, but then the negative flips it upside down. So if I do 2 to the -1, the negative is going to flip it and make it 1/2, and now it's just to the first power. So this will give us 1/2. Any number to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. So now that I have all of my values, now I want to go ahead and plot them so I can kind of look at this picture, right? So at -3, I'm at 1/8, which is teeny tiny, just barely above the 3 there. -2, I'm at 1/4, which is still pretty tiny, right? -1, I'm at 1/2. 0, I'm up at 1. 1, I'm up at 2. 2, I'm up at 4. And 3, I'm up at 8. So when I graph my dots or my ordered pairs here, then I want to go ahead and connect them with a line. Okay. All right. Now, I want to think about what would this graph look like if I kept picking more and more and more points, right? I could continue to pick bigger and bigger and bigger numbers, and that's just going to raise 2 to higher and higher and higher powers, right? Which is going to make this shoot up huge, right? Notice it's already taken a turn and it's gone from 2 to 4 to 8. The next one would be 16, then 32, then 64. So this is going to shoot up and just get huge, huge, huge. So now I want to think about, well, what happens if I go in the opposite direction? If I were to plug in extra negative numbers, right, I'm going to get those same values, but notice they're flipped. They're fractions. So I'm getting powers of 2, but they're in the denominator. So that means I'm going from 1/2 down to 1/4, down to 1/8, and then I would go down to 1/16, 1/32, 1/64, right? It's just going to get teeny, 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 tiny numbers as I get closer and closer and closer. So what happens is if the bottom of our fraction keeps getting bigger, then that's making our fraction get smaller, right? It's not making it 0. It's not making it negative. It's just getting smaller and smaller and smaller, which means it's going to keep getting infinitely close to this line right here, right, to the x-axis. Now, in math, if we get something that's exponentially close to something but cannot equal something, we call that line an asymptote. So we have this invisible line, if you will, right on the x-axis that is our asymptote. Okay, so we have an asymptote at y equals 0. The y equals 0 line is this line that these values are going to get closer and closer and closer to, but not actually touch or cross. Okay, and every exponential function has an asymptote. Okay, has a vertical asymptote. So it's important to be able to know what that is, to be able to identify it on your graph, and also to write it as an equation, y equals 0. Okay, don't just say 0 because it's a line. So you have to write it as an equation, y equals 0. Okay. And what's helpful for identifying where this asymptote is notice it's where my values are going to start getting teeny tiny. Because as they get teeny tiny, that means they're getting closer and closer and closer and closer to something, right? So when you're trying to identify the location of your asymptote, all you have to do is look at your table of values and see where your values are getting teeny tiny. Well, notice from 0 on, they start getting bigger, right? Over here, they're getting bigger. But if I look in the negative direction, these numbers are the little teeny tiny ones, which means that my asymptote is going to be closest to this end of my ordered pairs. So I always like to put an A there. That way, whenever I graph it, I know that this first point that I graph, that should be the point that's closest to my asymptote. That way I don't get confused and try to draw an asymptote up here by the last point, okay? All right, so let's look at another one. Let's look at one that has a larger base, or a base sorry, not larger, a smaller base between 0 and 1, and see how this graph will differ from the one we just did. Oh, I forgot to do domain and range. Just kidding. Let's look at this graph again. When we look at this graph, we also want to be able to identify our domain and our range. Okay, remember domain is how far is this graph going to go left and right. So if I look at this one, well, this one can keep going and going and going to the left, right? It may never cross this line, but it's going to keep going and going and going. I can plug in any negative number. So that means it will go back to negative infinity. As I look in the right direction, right, or in the positive direction, this is going to keep going and going and going and going, right, out to the right. So that means that my domain is negative infinity to infinity. Then I want to look at my range. Remember, range are our y values. So the lowest y value we can have here is really at this asymptote line, right, at 0. But we already talked about how our graph is going to come down here and never actually equal 0. So if it can't equal 0, but it can get infinitely close to it, the way that we express that interval notation is we go ahead and say it starts at 0, but we use a parenthesis to show that it's not including 0. Okay, it's as close as we can get to 0, but not including it. Okay, and then it can be anything bigger because obviously our y values go from 0 on up. Okay, all right. So now let's look at the other option of exponential decay and what this graph is going to look like. So I have the same values. I'm going to plug them in just like I did the last one. Plug these numbers into our exponent so that I get a nice little table of values. So if I plug in -3, I'm going to get 1/2 to the -3 power. The negative will flip it. So when I flip this one, I end up with 2/1 now to the +3. Now 2/1 is just 2, right? So what this is really giving me is 2 cubed, which is then 8. So notice what's happening is I know this is going to flip. Anytime I plug in a negative, it's going to flip, right? And then whatever my power is here, that's just going to be applied to the 2. So let's think about what that means for -2. -2 is going to flip it, right? So that I get 2/1, and then I'm going to be squaring it. So I'm going to write this one out too, but I'm not going to write the next one. So I flip it, which gives me 2/1, and 2/1 is just 2. So 2 squared gives me 4. So I just want to think through -1. Negative is going to flip it and give me 2/1, right? And then that raised to the first power is just 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 squared, remember we square the top and square the bottom, so that gives me 1/4. And then 1/2 cubed, 1/2 cubed gives me 1/8. Okay. So now that I have my table filled in, I want to go ahead and graph it and see what this one looks like. So at -3, I'm up at 8. -2, I'm at 4. -1, I'm at 2. 0, I'm at 1. 1, I'm at 1/2. 2, I'm at 1/4. 3, I'm at 1/8. So notice when you connect your dots here, the shape is very similar, right? Very similar. The only difference is from our last graph to this graph, our first graph was increasing, right? Because as our x's increase, that means the power of 2 increases, which is going to shoot up huge, right? But now that we're dealing with a small fraction base here, right? As we increase our x's, that's actually going to make this fraction teeny tiny, right? So it's a decreasing function. But those teeny tiny values are still getting closer and closer and closer to 0 and not touching, which means that on this graph, we also have an asymptote at y equals 0. Okay, so I'm going to go ahead and draw that dotted line in and write down here that we have an asymptote at y equals 0. Okay, every exponential function has an asymptote, every single one. Okay, it's where those values start getting tiny, 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 tiny. That means they're approaching something that they're not going to be able to touch. So on this one, if I identify where my values are getting tiny, it's where these little fractions are, right? So that means this last point should be the point closest to my asymptote, right? And notice here it is. So if it helps you to make that little note to help you remember where it is, you're more than welcome to do that. Okay, so now let's go ahead and identify our domain and our range. Our domain, notice, is left to right. This function is going to keep going out to the left. It's also going to keep going out to the right. In fact, every exponential function, no matter, even when you transform it, if you move it left, right, up, down, stretch, shrink, reflect it, okay, it will always keep going left and right. So our domain on these functions should always be -infinity to infinity when we're dealing with exponential functions, okay? However, our range will always have a restriction because we're always going to have that horizontal asymptote, which means that the lowest that this graph is going to be able to go here, again, is 0, not included, because there's an asymptote there, right? And then anything bigger than 0. All right, so there is one on the next page, a practice problem for you guys to try. So go ahead and pause the video and work out that practice problem, and then when you're ready to check yourself, play the video again. So here is our practice problem. When you plug in -3, you get 27, -2, you get 9, -1, you get 3, 0, you get 1, 1, you get 1/3, 2, you get 1/9, and 3, you get 1/27. Okay, now all of these you can graph except for that first one, right? 27 is off this graph, so we're just not going to worry about that. Okay, we're just going to graph these other remaining ones. But we do want to try to get at least 5 points on our graph. So even if you needed to add on 4 or whatever you want to do to make sure you get at least 5 points, because the more points you have, the more extreme that curve goes, and it's easier to see where the location of your asymptote is. Okay, so here when we plot these points, you can see this is a decreasing function, right? It should be exponential decay because our base is between 0 and 1. We still have an asymptote here at y equals 0, and our domain, as always, is going to be -infinity to infinity, and our range is from 0 to infinity. Okay, all right, so now we have the basic idea of how to get that parent function. This is the most basic form of this function. No transformations have been applied. Nothing's being added, subtracted, multiplied. This is what we call a parent function. So this is what, this is what you're going to have to come up with when you graph these, is identifying what is the number here that has an exponent, or what is that base. And then once you know the base, you're going to create this parent table off of it, and this is going to be the first table you start with when you do your transformations. Okay, all right, so with that being said, anytime we want to transform any function, we need to make sure that we understand where our transformations are taking place and what they represent, right? This is the same transformations that we went over in Unit 7, our HSRV shifting, right? But here we're dealing with exponential functions, which look like f of x equals b to the x power, where b is whatever our base happens to be for that problem, okay? So when we transform functions, it's important to know, are our transformations happening inside the function? So we know they're being applied to the x, right? Or are they happening outside the function? Because then we know they're being applied to the y. So when we have a square root function, for example, whatever's inside the square root is being applied to the x, whatever's outside the square root is being applied to the y. The same thing is true with exponential functions, except notice where x is not under a square root, right? X is up here in the exponent. So anything being done in the exponent is what we will call being done inside the function, okay? So anything in the exponent affects the x. That's where our left-right shifts are. That's where our reflections involving negating the x will be. That's where our horizontal stretching and shrinking will be, is wherever that x is, which is inside the exponent, okay? If it's something that's going to be applied to the y, then it has to be outside the function, or in this case, outside the exponent. So anything being added, subtracted, multiplied outside the function is going to be applied to the y value, okay? So I want to go ahead and just talk through these examples. So this example, I'm looking to see, first of all, what's my parent function, and then what transformation has happened. So all I'm looking at is for my base. Okay, my base here that has an exponent is 2. So my parent function here would be 2 to the x. And notice the only thing that has changed from this being just a basic old 2 to the x is the plus 5. The plus 5 is in the exponent, so that's inside the function, which means it's going to affect the x. And that's actually going to be a horizontal shift. X's are backwards, right? So that's going to be a horizontal shift to the left 5. Okay. Same thing on the next one. Notice my parent function is still 2 to the x, but this time I have this multiplication of 4. Now the 4 is not in the exponent, so it's not inside the function, it's outside the function. And if it's outside the function, that means it's affecting the y. Okay. So if I have a multiplication of 4, that's actually going to vertically stretch my exponential graph. Okay. Let's look at this next one. Again, my parent function is 2 to the x because 2 is the thing that has the exponent. And the only transformation here is this minus 7. Now this minus 7 is not taking place inside the exponent, so that means it's outside the function and being applied to the y. So that would be a vertical shift down 7. Okay. And then this last one, we have a negative. It's the only thing keeping it from looking like its parent function, which is just 2 to the x. And that negative is inside the function because it's in the exponent. So that means we are changing the signs of our x's. And if we're changing the sign of our x's, that's going to be a reflection about the y-axis. So all of our transformations are the same as when we did transformations in Unit 7. The only difference is we're doing them with an exponential function, right? All right, so let's go ahead and look at how we're going to transform these. Let's look at one. Very important because there is a worksheet with this section. Notice here it says graph each of the following exponential graphs by identifying all transformations. So you want to state the transformations just like we're going to do in our notes, and then transforming the graph with XY tables at each step. Okay, that's how I'm going to grade your paper, is not did you plug this into a graphing calculator and sketch a picture. It's going to be did you identify the transformations and then modify an XY table for every single transformation you have. Okay, so be sure you do that. Then once we get it graphed, then we're just going to identify domain, range, and asymptote. Okay, be sure to go ahead and put that dotted line wherever your asymptote is for 2 reasons. One, it's good for you to put that dotted line because it's a visual reminder that there should be one. And secondly, because your graph can't cross an asymptote, putting that asymptote actually on your graph will help your graph to look a little bit more accurate because it will ensure that you don't draw the line past where it should be. Okay? All right, so let's look at our first one. Now, before we start doing any type of transformations or identifying transformations, I want to first identify what is my parent function, or what's the most basic form of this f of x function. And in order to do that, all I have to look at is what has the exponent, right? Here, the thing with the exponent is a 2. So that means that my parent function is 2 to the x power. Okay, so before I do any transformations or anything, I want to go ahead and create an XY table for 2 to the x power. That way I have my starting points that I can begin graphing. Okay, so I'm just going to pick -2, -1, 0, 1, and 2. You can always do more. I know on the examples we did on the last page, we did -3 and 3. Okay, you can always add additional ones. But for the purpose of this one, I'm just going to do 5. Okay. All right. So when we plug in these, 2 to the -2 is going to flip it and square it. So flip it gives me 1/2. Square it gives me 1/4. -1 is going to flip it, which gives me 1/2. 0, 2 to the 0 is 1. 2 to the first power is 2. And 2 squared is 4. Now I will say I always do mine with fractions. But if you're plugging these in using your calculator, okay, if you do 2 to the -2 and you get 0.25, you can have decimals in here. Okay, if you're okay with graphing your function with decimals, I don't care whether you do fractions or decimals, okay, as long as it's equivalent. All right, so now we have our starting points. We know what our original function looks like. Now we need to do those transformations. So let's go ahead and come up here and say HSRV, because remember we have to do them in that order. And I only see 2 transformations for this function. I see the +1 in the exponent and the +3 outside the exponent. So the +1 in the exponent is happening inside the function. So that's going to be a horizontal shift. X's are backwards from what we would think, so that's going to move us left 1. So we're going to go left 1. And the way that we're going to modify our chart to move all of our values to the left is we're going to take our x's and subtract 1. Okay. And then this +3 on the outside here, since it's outside, it's affecting the y's, that's going to be a vertical shift up 3. So in our tables, we're going to take our y's and we're going to add 3 to them. So we have no stretching, no reflecting. Okay. All right, now remember we want to do our transformations in HSRV order, which means I'm going to do my horizontal shift first, and then I'll do my vertical shift. So if I shift this horizontally, now my function looks like 2 to the x plus 1. So I'm going to draw my little table here. And we know that to move left 1, when we modify our table, we have to take our x's and subtract 1. So I take my x's from the previous table and subtract 1. So -2 minus 1 is -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. And 2 minus 1 is 1. Okay, we didn't do anything to the y's, so they stay the same. 1/4, 1/2, 1, 2, and 4. And then I want to do my vertical shift. 2 to the x plus 1, now +3. And when I do my vertical shift, all I have to do is take my y's from the previous table and add 3 to them. So again, in your calculator, 3 plus 1/4, you can write this as 3 1/4 or 3.25. Okay, whether you prefer fractions or decimals doesn't matter to me. Okay, 3 plus 1/2 is 3 1/2. 3 plus 1 is 4. 3 plus 2 is 5, and 3 plus 4 is 7. Our x's stay the same. -3, -2, -1, 0, 1. Okay. All right. So now that we have all of our points, I want to go ahead and graph it so that I can find my asymptote. Now, remember, our asymptote is where those points get 0, like close and close and close, smaller and smaller and smaller, closer and closer and closer to 0. So I'm going to go ahead and just look over here. On my original parent function, you can see where my y values are getting smaller and smaller and smaller is up here towards the negative direction, right? So I'm going to go ahead and just put my little a right there. That way I know the asymptote should be on that end. Now, as we transform our tables, it's still true. This point should still be the one closest to the asymptote. Okay, so let's go ahead and graph our pictures, our points, sorry, and see where it's at. So at -3, I'm up at 3 1/4, so that's going to be just barely above 3. At -2, I'm up at 3 1/2. At -1, I'm up at 4. 0, I'm up at 5, and 1, I'm up at 7. So you can see with 5 points, we get a really nice shape. Okay, if you only do 3, you don't get a very nice shape. And remember, this first point was the one that was going to be closest to the asymptote. So I can look, I'm going from 4 to 3 1/2 down to 3 1/4. So I can see this is getting closer and closer and closer to this y value of 3. So 3 is where my asymptote line is going to be. So go ahead and draw it in. Make sure you write it as a line. Don't just say 3. Okay, say y equals 3. And then we can go ahead and identify our domain and range. We know that our domain of any exponential function is going to keep going left and right. So that's going to be -infinity to infinity. And our range is always going to be cut off because there's always going to be an asymptote. So notice here, our lowest y value is +3. And our highest y value, it's going to keep going up all the way up to +infinity. Okay? Let me look at a couple more, and then y'all will get a chance to do some. Okay? So really, just to throw this out there right now, really all of this is exactly what we did in Unit 7. We know how to identify transformations. We know how to modify tables. We know how to find domain and range. So really the only new thing is identifying what the exponential base is, right, the exponential parent, and creating that table, and then also identifying the asymptote. So hopefully not too challenging, right, since most of it is stuff we've done before. All right, let's look at another one. So here we have f of x equals 4 times 1/2 x minus 2. So the first thing I want to do before I identify any transformations or anything like that is I want to go ahead and identify what is the exponential parent function, or what's my exponential base here. So notice the thing with the exponent is 1/2. So that means that my parent function is going to be 1/2 to the x power. That's the most basic form of this function. So I'm going to go ahead and create a table using 1/2 to the x. And again, I'm just going to pick -2, -1, 0, 1, and 2. So when I apply these numbers to the exponent, 1/2 to the -2, that's going to flip it and square it, which will give me 4. 1/2 to the -1 is going to flip it, which is 2. 1/2 to the 0 is 1. 1/2 to the first power is 1/2. And 1/2 squared is 1/4. Okay. Notice this is the end where I see my y values getting teeny tiny, right? So on this one, I know my asymptote is going to be closest to this point. Okay. All right. So now let's go ahead and identify what transformations have happened. So when I look at this, I see that I have this 4 out front and I have a -2 at the end. Both of those are not in the exponent, which means it's not affecting the x. So we can rule out horizontal already. Now the 4 out here being multiplied, that's going to be a stretch or a shrink. Since I'm multiplying by a large number, it's going to vertically stretch it. So vertically stretch. So in our table of values, I'm going to take my y's and just multiply them by 4. Okay. The only other transformation we have is the -2, which is going to be a vertical shift down 2. So I'm going to take my y's, subtract 2. Now, even though both of these things are being done to the y, it's still important that you do your transformations in HSRV order, meaning we have to do our vertical stretch first and then our shift down. Okay. So when I do my vertical stretch, now my function is going to look like 4 times 1/2 to the x power. Okay. And I'm going to create a table. and modify it by taking the y's from the previous table and multiplying them by 4. Okay? So when I multiply my y's by 4, 4 times 4 is 16, 4 times 2 is 8, 4 times 1 is 4, 4 times a half, or 1/2 of 4 is 2, and 1/4 of 4, or 4 times a fourth, is 1. Okay. So I'm going to go ahead and fill in my x's because they did not change. And then I do my vertical shift down 2. So 4 times 1/4 x minus 2. So I'm going to take my y's from the previous table and subtract 2 from them. Okay. All right, so when I subtract 2, I'm going to get 14, 6, 2, 0, and -1. Okay. My x's stay the same. -2, -1, 0, 1, and 2. So now that my function looks the way I want it to, I know this is going to be the side closest to my asymptote, right? So at -2, I'm up at 14. Well, that one's off the graph. So if it's off the graph, we don't have to worry about plotting that one. Okay, so let's start with -1, 6, 0, 2, 1, 0, 2, -1. Okay, now notice here, I can go ahead and combine these, but it makes it a little bit hard to see where my asymptote is, right? Because before we looked for where are our numbers getting teeny tiny, right? So if you can't really tell, well, we can tell it's going to be this side because we wrote our A. We know the asymptote should be over here. And notice it's dead on 1. So if it equals 1 right now, we know our asymptote isn't at 1. It has to be approaching the next value. Okay, so the next value that it could approach would be 2. Okay, you can take my word for it. Or if you want, you could always plug in an additional number here, right? I could plug in 3 and get 1/8. I could go ahead and multiply 1/8 by 4 and get 1/2, right? And then I could take 1/2 and subtract 2, and I would get -1.5. So -1.5 is what I get there. And then that makes it a little bit easier to see we're actually approaching 2. Okay. All right. So this means that our asymptote is down at -2. So we're going to write that as y equals -2. Then we're going to list our domain, which we know for all exponentials is -infinity to infinity because it's going to keep going left and right. And our range is our lowest y value, which in this case is now -2 up to infinity. And we use parentheses because it cannot equal -2. Okay. All right, I have one more to do, and then I will let y'all try some. So let's look at the next one on the next page. We have f of x is equal to 3 to the -x minus 3 plus 2. So I am going to list my HSRV, but before I do that, I want to go ahead and identify my parent. Notice the number that has an exponent here is 3. So that means that my parent function is 3 to the x power. So I'm going to go ahead and make my table of values, -2, -1, 0, 1, and 2, and plug those in. When I do 3 to the -2 power, that's going to flip it and square it, which will give me 1/9. When I do 3 to the -1 power, I get 1/3. 3 to the 0 power is 1. 3 to the first power is 3, and 3 squared is 9. So now I have my starting function, my starting points. Now I can identify my transformations, and I have 3. I have the negative, the -3, and the +2. So the negative is going to be a reflection. So I just need to know what it's a reflection about. So notice my negative is in the exponent, which means I'm negating my x's. If I change the sign of my x's, that's going to rotate it or reflect it about the y-axis. Okay, so in my tables, I'm going to change the signs of my x's. Okay, Then I have the -3 happening in the exponent, which is going to be a horizontal shift to the right 3. So I'm going to take my x's and add 3 to them to modify my tables. Okay. And then the last thing I have is the +2, which is outside the function. So that's going to shift me vertically up 2. So I take my y's and add 2 to them. So no stretching. Okay. All right, so let's go ahead and start transforming. So notice here, I'm going to go ahead and put where my y values are getting teeny tiny, that's where my asymptote is. So that means the asymptote is closest to this side right now. Okay. So I'm going to do these transformations in HSRV order. So I do my horizontal shift first. So this looks like 3 to the x minus 3. So I'm going to go ahead and add 3 to my x's from the previous table. So -2 plus 3 is 1. -1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. And 2 plus 3 is 5. My y's stay the same. 1/9, 1/3, 1/3, 9. Okay. Then I do my next transformation, which is about the y-axis. So that's where we get our negative in front of the x. Okay. To do that transformation, I'm just going to take my x's from the previous table and change their sign. So now I have -1, -2, -3, -4, and -5. My y's stay the same. So 1/9, 1/3, 1/3, 9. And then my last transformation is my vertical shift up. So I have -3 to the -x minus 3 plus 2. And I'm going to take my y's from the previous table and just add 2 to them. So I'm going to get 2 and 1/9, 2 and 1/3, 3, 5, and 11. Okay. My x's stay the same. Okay. And we know, because we noted over here, that our first order pair should be the closest to the asymptote. So the same thing is true over here. Okay. So let's go ahead and plot our point so we can see what it's approaching. So at -1, I'm up at 2 and 1/9. 2 and 1/9 is just barely past 2. At -2, I'm at 2 and 1/3. At -3, I'm up at 3. -4, I'm up at 5. And -5, I'm up at 11, which is actually off my graph. Off the graph. So we can't plot that one. So I'm going to go ahead and bring these down. I think it's pretty easy to see that my y values here, or my asymptote, is approaching at 2, which means my asymptote is at y equals 2. And then we just need to identify our domain and our range. Domain, we know this function is going to keep going left and right. Our range here, or our lowest y value, is at 2, and it's going to continue on up to infinity. Okay? All right, so there are 3 for you to try. Go ahead and pause the video, and whenever you're ready, play it, and we'll go over them and see how you did. All right, so on our first one, we have 2 shifts, left 2 and up 1. Our parent function that we're starting with is 3 to the x, because 3 is what has an exponent here. So you need to make your table with 3 to the x. And notice it's on the negative side that our y values are getting smaller and smaller. So that's where our asymptote is going to be. And then we just modify. We subtract 2 from our x's to move it to the left 2. And then we add 1 to our y's to move it up 1. So our function should look something like this, with an asymptote up at +1. That means our domain is -infinity to infinity, and our range is 1 to infinity, always with a parenthesis here because we have an asymptote at that number. Okay, and our asymptote is at y equals 1. If you need to spend some more time on this, feel free to pause it. Otherwise, we're going to go ahead and move on to the second and third problems. So number 2, we have 3 transformations. We have the negative on the front, which is negating the y's, which is a reflection about the x-axis. Okay. Then we have that 2 that's being multiplied outside, which is being applied to the y. So that's a vertical stretch. So we're going to multiply our y's by 2. And then we have the other negative in the exponent. Okay, the other negative in the exponent is negating the x's, which, excuse me, is going to reflect it around the y-axis. Okay, so those are our three transformations. Here, the number or the base, right, that is stuck with this exponent is 2, which means my parent function is 2 to the x. So I'm going to make my table based on it. I can see that my small values are over here on the negative side, so that's going to be the point closest to my asymptote. And then I go ahead and modify my tables. So we have to do this in HSRV order. So we do our stretch first, so we multiply our y's by 2, and then we do our 2 reflections. Now, since reflections are on the same level of our order of transformations, I don't mind if you do them in the same step. If you had 2 tables here, that's totally fine. Either way, we need to change all the signs of our x's and all the signs of our y's, and these are the values we should end up with. So when you graph your picture, it looks something like this, okay? With our asymptote still at 0 because we didn't move up or down, right? We didn't have a vertical shift. So domain is negative infinity to infinity. Our range, this one's a little bit different because we always do our lowest y value to our highest y value. So here our lowest y value is negative infinity, and it's going to come up and hit the asymptote at 0. Okay, so it cuts off our range at 0, again with a parenthesis, which means our asymptote is at y equals 0. Be sure you have your y equals. Okay, all right, and then number 3, same idea, identify the base, it's 1/3. So we're going to start with 1/3 to the x, make our table based on those values. Feel free to use your calculator if you're having a hard time with these exponents. Okay, you'll be able to get a decimal or even a fraction when you plug them in. Okay, and then we identify our transformations. Here we had 2 transformations. The -4 in the exponent moves us to the right 4, and the -5 outside the function moves us down 5. So we're going to add 4 to our x's to do our first transformation, and then we're going to subtract 5 from our y's to do that second transformation. So this is our ending table of values. When we plot our points, we should get a decreasing or an exponential decay problem because our base was between 0 and 1, right? And our asymptote is down here at -5. Make sure you draw in the dotted line to show where your asymptote is and that you also have it stated down below. Okay. Domain is negative infinity to infinity. Range starts down here at -5 and then continues on up to positive infinity. Okay. All right. So that is the end of exponential function graphs. So you now should be able to do that assignment in your Alta Newton homework. You also have a worksheet that goes along with this, okay? On your worksheet, I'm going to be grading you based on that you've identified your transformations, you created your parent table, and you modified that table with a new table for each transformation. Okay, so make sure you work these on your worksheet the same way we did in class so that you don't miss points or credit. Okay, if you have any problems, please let me know. I'm happy to help.